It's my pleasure to welcome Helen Durand from Wayne State University. Helen got her degrees from UCLA in chemical engineering. Then she joined Wayne State, and she has been a very successful researcher in the area of CPS. She won both Air Force and NSF Career Awards and other research excellence awards from Wayne State. And I met her in NSF CPS meetings, and I thought it would be great to have her here today. Please welcome Helen.
Thank you very much. So I'm very excited to be here today, and I'll be presenting our group's work related to cybersecurity and quantum computation for control of cyber-physical systems for next-generation manufacturing. I'm going to start off by talking about why we use process control in chemicals manufacturing. So when we have our chemical process, which is our chemical manufacturing plant, it's supposed to convert raw materials into products. And so when we do this, we have a lot of objectives: doing this safely, meeting the environmental regulations, meeting the product specifications, and making a profit. And so in order to meet all of these objectives at once, we need to continuously monitor our process and then externally intervene if any of our objectives is not being met. And process control is the way that we do this in an automated fashion. In the chemical process industries, it's very common to use feedback control loops with the form shown here, where we will have our variable that describes the condition of our process. So in chemical engineering, that will be things like temperature, pressure, species concentration. These are our outputs. These get measured by the sensor and then compared against the set point, the value that we want the process output to take. And the error between the set point and the output goes to the controller, which then uses the algorithm in order to determine what the actuator, which for chemical processes is often something like a valve, should do in order to try to reduce the error for the process. In undergraduate control, we will typically teach our undergraduates about proportional integral derivative, or PID control, as the control law being executed here. And this is very ubiquitous in chemical plants and has the control form shown here, where the input is equal to these terms that are proportional, integral, and derivative of the error. But proportional integral derivative control isn't able to handle everything. And so advanced process control designs can be looked at for chemical processes. And these might use a process dynamic model explicitly in the control design, where the mathematical process model comes from either first principles, which for us would be making models using things like mass and energy balances, or we can identify this model from input-output process data. And the model will then describe our process dynamics, and we can make controllers based on our process model. In chemical engineering, we very typically use nonlinear models. And the reason for this can be exemplified by looking at this reactor that we have here. This is what we call a continuous stirred tank reactor, or CSTR. And this is one of the special types of reactors that we teach our undergraduates about in chemical engineering. It's a well-mixed, actually perfectly mixed tank. And so it has this feed, which here consists of our reactant A at the reactant concentration Ca0 and at an inlet feed temperature T0. It goes into this tank and it's perfectly mixed. We can add in some heat. And then what comes out is the concentration of the reactant and temperature T that are equal to what was in our tank because it was perfectly mixed. So if we try to model this with mass and energy balances, we get the system of nonlinear ordinary differential equations that's shown here, showing how the temperature and concentration of our reactant in the reactor are changing with time. And we can see some nonlinearities, particularly in this expression that has an exponential related to the temperature and being multiplied by the concentration of the reactant. And this is actually the reaction rate law. So this is why in chemical engineering, we often end up with nonlinear models, is that one of the distinct features of chemical processes is that we're going to perform reactions. And a lot of times these reactions will end up introducing nonlinearities into our models. And so we'd like to be able to develop general controllers that can handle a wide variety of reactions and different chemical processes that we might want to handle. And so to do that, I'm going to define this notation for our system. X here is the vector of process states, which for this example would be our temperature and concentration of our reactant. X dot is its time derivative. U is our inputs to our process, which for this example might be the heat if we're able to adjust that into our reactor. And then W is our vector of disturbances, which in this example, if, for example, the reactant concentration in the feed was changing, maybe due to our feedstock not being uniform, but we're not able to actually adjust that, now it's our disturbance. So with this, the notation I'm going to be using in the rest of this talk to represent a system of nonlinear ordinary differential equations that can describe many different chemical processes is as shown here, that the time derivative of our states is equal to a nonlinear vector function of our states, inputs, and disturbances. And there are a lot of techniques you could use to try to design controllers for this system, but the type that I'll be focusing on is called model predictive control. And so before I overview model predictive control, I'm going to first give a little bit more background on what class of systems we're considering. The class of systems that we're considering is such that the state, the input, and the disturbance are all bounded. And we assume that the system is stabilizable in the sense that there exists an explicit stabilizing control law, h of x, that can render our origin asymptotically stable, in the sense that there exists a Lyapunov function v, for which its time derivative along the state trajectories under the controller h of x, and in the absence of disturbances is negative for all x in a neighborhood d of the origin. And then we'll define a level set of our Lyapunov function, which is shown here within this region D. And I'm going to call this the stability region omega rho. And so this is a region where we can stabilize the process for all states within the stability region using the controller h of x in the sense that we can drive the state toward the origin. And then so brief background on model predictive control in case there's anyone who's not familiar with this specific type of control law. It is an optimization-based control framework in which we minimize an objective function subject to a process dynamic model that enables us to make predictions into the future, a measurement of the process state that is used to initialize this process dynamic model, and then we can also incorporate constraints like the constraints on the input and the state that are shown here. Often in chemical processes, we would use a quadratic tracking stage cost because often we want to operate our chemical processes at a steady state in order to be able to ensure that our products meet the required specifications from the customers. And so this would be an example of what the objective function might look like. And then we solve the optimization problem every delta time units. Delta in this notation refers to our sampling period. So we solve it at every sampling time tk. And the solution is then a piecewise constant input trajectory where we hold each piece constant for a time period delta, and we have a prediction horizon of length n. So this figure shows all of that. It shows making predictions of the state, which are these dotted lines, which approach the steady state ideally, and then figuring out which inputs to apply and sample and hold throughout the prediction horizon, where we have over one sampling period, we're able to hold it constant and then change it, and there will be n sampling periods for the prediction horizon. And then we're going to apply this in what's known as a receding horizon implementation. So we're going to calculate all the pieces and then only apply the first piece of the input trajectory in order to get feedback to account for the plant model mismatch between this model that the MPC is using in order to predict what the states will be in the future and what the actual plant dynamics are. And so even though we're going to only apply the first piece of the input trajectory, it still could be true that having the longer prediction horizon could help improve closed loop performance in the sense of enabling the state to be driven toward the steady state. But this idea of having the state being driven toward the steady state or closed loop stability isn't actually guaranteed theoretically for the formulation as written here without some additional conditions or constraints. So there are a lot of approaches then for being able to guarantee closed loop stability for model predictive control. And these include doing things like using an infinite or sufficiently long prediction horizon, terminal costs or constraints, or a constructive constraint. And so that's some background on model predictive control in the process industries. Now I'm going to talk a little bit more about how it's used today. In cases where MPC is used in chemical manufacturing, this is often how it would work. So you would have a steady state economic optimization problem known as real-time optimization that computes the economically optimal steady states for the process to operate at, and then sends those to the model predictive controller that has that tracking objective function. So it would then have its minimum at this economically optimal steady state. The tracking MPC would then try to drive the state toward that economically optimal steady state, and that would be how the process behaves. But in recent years, maybe about the last 15 or so, there has been a rethinking of this and saying, why are we keeping these two layers apart? Instead of separating economic optimization and control like this, could we combine them better? So could we actually make our model predictive controller optimize economics instead of only optimizing this tracking objective function and trying to force steady state? So this idea is known as economic model predictive control, or EMPC. It's really actually the same thing as MPC, except that you just allow a general objective function. But that could have very significant implications in that now, if your objective function isn't a tracking objective function anymore, you might get dynamic or time varying operation under this type of input policy instead of just driving the process state to the steady state. And so this idea where you could have potentially non-steady state objective functions might be useful if you have cases like a time varying objective function due to maybe something like electricity costs varying throughout the day or time varying constraints for similar reasons. So economic model predictive control really is just making model predictive control more general. So the formulation looks basically the same as the model predictive control formulation discussed earlier, except that we now allow ourselves to have any objective function we would like. It doesn't necessarily need to be quadratic. And we still have a dynamic process model, a state feedback measurement, input and state magnitude constraints. And of course, you can add any other constraints you would like. Here I added input rate of change constraints for illustration that you can add all kinds of other things if you would like. So the main idea about economic MPC is that it gives you the flexibility to compute control actions that optimize economics. And so this can be cool, but then the problem is now what are you going to do about the stability concern? So the theoretical concern about how do you guarantee safety? And so just like we said for model predictive control earlier, there are many different approaches you could take for this. But the type that we often focus on in our group is what's known as Lyapunov-based model predictive control, or I'll call it here LEMPC for Lyapunov-based economic model predictive control. And then this is from the group of Panagiatis Christofides at UCLA. And it looks basically the same as the economic model predictive controller on the prior slide. We still have our general cost function, our dynamic model, a state measurement, input and state constraints. But now we have this new type of constraint. And these ones are based on the Lyapunov function and the explicit stabilizing controller h of x. And they allow us to be able to ensure that the process state is always maintained within a known operating region. So instead of like before, where we said the objective was only to operate at steady state, this formulation allows us to either do that or to instead just say optimize economics within this larger region. So it doesn't have to be steady state anymore, but we can still guarantee some notion of safety if safety means that we stay within this region omega rho. And so the idea would be that we use this first constraint that's shown in red to say that if the process state measurement is within this smaller region, omega rho e, then what that means we should do is make the state predictions stay in this region. But since there might be plant model mismatch, the actual state might go out. So we don't want it to go all the way out of our safe region. So instead, then we'll switch to the second constraint that drives the state back toward lower Lyapunov level sets and will bring us back toward the origin. And by trading off between these two, we achieve the goal of maintaining the closed loop state within this region omega rho, and then also being able, if we want to drive the Lyapunov function to lower values, which means that if we wanted to do steady state tracking, we still could if we just enforce this second constraint all the time. And so you can think of this region omega rho sort of like safety. So you keep your concentration, for example, and your temperature in a known region. So you're not allowing things like reaction runaway, where maybe your temperature is going really crazy, and then you're getting issues with the pressure building up in your vessel exploding. So by keeping it in the safe operating region, that helps you maintain safety. So that's the background on the types of control laws that we're going to be considering in this talk. And I'm now going to move into some of the work that we've been doing related to cybersecurity for process control systems and using quantum computing in order to implement control laws. And so I'm going to start by just giving a little bit of background on cybersecurity and process control. Cyber attacks on control systems seek to impact a physical process and can impact things like safety, profit, and production rates. So we might ask, do cyber attackers actually care about attacking our control and manufacturing systems? And the answer is yes. And how can we tell? Well, there are examples of cases where control and manufacturing systems have been attacked. And one very famous example is what's called the Stuxnet attack from 2010. This was an attack on Iranian nuclear facilities where a worm entered systems via USB sticks and spread, searching for control system software. It then ran centrifuges at conditions that caused them to break down and was falsifying information so that people couldn't tell this was happening. So given that having attacks on control and manufacturing systems is a real issue, what are ways that we can make it hard for cyber attackers to cause problems for our plants? And there are a lot of things we could do. We could design the process to be attack resilient. We could try to look at detecting attacks, shutting down our processes, diagnosing attacks, seeing if you can fight back against the attackers. But overall, you would want to try to figure out how could you do this while preventing reductions in agility for manufacturing. So in order to try to move toward that broad goal, there's a need to understand the control theory of attacks and the mitigation strategies. And so the first thing we can do is say, what are cyber attacks? And mathematically, what they would be is something that removes the associations between our state measurements and our inputs. So essentially now, any undesired inputs that are in my input bounds could be applied at a given state. But attacks can occur on sensors, actuators, or both. And when I say that, in our group, we haven't really been considering the method by which these attacks occur. When we say, for example, there's a sensor attack, what we mean is that for whatever reason, the controller is getting wrong measurements and that we don't say exactly how it got those. We're just saying that's the situation. And then similarly for the actuators, for whatever reason, the inputs to the process are wrong, however that happened. And so this would be an example of what the block diagram from earlier might look like if we were to have false state measurements. So now the sensor to the controller link is, for whatever reason, not correct. And so if we wanted to have state measurement falsification and say, what would it mean to have cyber attack resilience? We could try to make mathematical definitions of that, like, oh, you wouldn't have any unsafe states at any time, no matter what disturbances you have, and things like that. But that's not very constructive for figuring out how would we do this. So our group's approach so far has been to try out different ideas for detecting attacks and designing control strategies that are related to those detection strategies to see how they work, and then analyze the benefits and limitations of the different approaches to get a better handle on what can we and can't we do with different control designs and why, and with the hope that that will lead us towards suggesting better things for how to actually make a cyber attack resilient process in the future. And so we've looked at 3 different concepts in the context of utilizing Lyapunov-based economic model predictive control to attempt to detect attacks. And the reason that we like using LEMPC is because of some of the theoretical properties that it has that we think elucidate to us a lot of properties about how systems that are subject to disturbances, measurement noise, and so forth are able to behave and be stabilized. And so we think that this gives us a lot of insight broadly into understanding how these cybersecurity policies might work. So some of the strategies we've looked at have included LEMPC with random control law modifications to probe for cyber attacks. This is what would be known as an active cyber attack detection strategy, because it's actually changing the control law at different times in order to try to figure out if there's an attack by checking if the Lyapunov function is decreasing or not when it should be. And so we were able to prove different things about this. So for example, we were able to prove that you would always have safety when there were actuator attacks if you were using this policy and you didn't detect them, but you didn't always guarantee safety if instead the attacks were on the sensor measurements. And then we had a state feedback LEMPC with an attack detection strategy based on state predictions at each sampling time and guaranteed safety under the actuator attacks again, but only for a short time if we couldn't detect the sensor measurement attack. And we also had an output feedback LEMPC with an attack detection strategy based on redundant state estimators. So what I'm going to do is overview this strategy to give a highlight to some of the ways that these things work and how we're designing control laws in tandem with the detection strategies in order to try to figure out how we can make safety guarantees and when we can do so. So to give an overview of this strategy, I'm going to make some additional assumptions. So we're going to assume that there are M sets of measurements, and these are continuously available, and we can have some sensor noise that's represented by this VI term here. And we assume that a deterministic observer exists for each of the M sets of measurements, and that the observer state at some point in time becomes sufficiently close to the actual state in this sense that's shown down here, where the norm of the difference between the observer state and the actual state is less than or equal to an upper bound. We assume that that time at which it converges is before the attack occurs on the sensors. So now we're going to design this LEMPC that's shown here. It's the same one as earlier, except that now we use the state estimate that's noted here. as our initial condition for the dynamic model instead of a state measurement. And then the idea is that cyber attacks on the state measurements would then impact the state estimates that are being used by this LEMPC. And if the estimate is sufficiently incorrect, the closed loop state could exit the stability region. But we have the estimator properties, and from this we can suggest an attack detection methodology. So specifically, as noted, we assume that for each estimator, there is a time after which the estimate and the actual state become less than or equal to this upper bound. So they become close enough to each other, and we can characterize how close that is. And then this would imply that if all the estimates achieve this level of closeness to the actual state, all the estimates should actually be pretty close to each other also. So then we could say, well, how close should they be? And we could set this upper bound theoretically, and then say the difference between two estimates should be no more than a certain amount when no attack occurs. This then can be used to help us flag when an attack occurs. So specifically, if we consider that at least one state estimate is not impacted by an attacker, then if the difference between two estimates is greater than this value of epsilon max that it should never exceed if there's no attack, we flag an attack. And then if the difference between the estimates is less than or equal to this upper bound, then either we don't have an attack or we do. And so let's say that we do, but we didn't detect it because it falls under the radar of our detection strategy. In that case, we're actually able to demonstrate that the closed loop state will always be maintained in the safe operating region omega rho, as long as we have some sufficient conditions over the subsequent sampling period. So this enables us to start looking at how can we design these different strategies for detection in tandem with the control laws so that we can at least do some level of safety for some amount of time after we don't detect attacks, because we're able to combine the control theory with the detection strategy. And so in this last part of what I wanted to talk about cybersecurity, I'm going to show an example that helps clarify how cyber attacks are different from faults. And so in this case, we're going to look at the idea of what if we didn't have only an attack on our sensors? What if we had an attack on the actuators and the sensors at once? And so in order to look at this, we're going to consider our continuous stirred tank reactor with a second order A to B reaction. And we have the dynamics shown here. Then our control objective is to optimize our process economics while maintaining the closed loop state in a safe operating region. So here is our economic metric. This is the time integral of the reaction rate. So this should represent some level of production. And we'll have this manipulated input constraint that our input is the reactant concentration in our feed, and it has to be within these bounds. And from that, we'll design a Lyapunov-based controller and our stability region so that we can design our LEMPC. And then we're going to assume that the LEMPC gets a measurement of both states, the concentration of the reactant and the temperature in the reactor. And we're going to initialize an attack detection policy. And here's what it's going to be. Check if the Lyapunov function decreases over the sampling period when we evaluate it based on the measurement that we're getting from the sensors. And so now we can look at some different types of attack policies and try to better understand from this what's the difference between a cyber attack and a fault. So here we can look at this first example. Let's say we have an actuator attack only. And in that case, we just have this actuator output. Let's say it's just fixed to some value. Could we detect this attack based on our detection strategy that checks whether the Lyapunov function is decreasing? So here on the left, what we have is it says actual V1. This means the actual value of the Lyapunov function along the actual state trajectory. On the right, it says the evaluated value of V1. This means the value of the Lyapunov function if we evaluate it at the state measurements we're receiving from the sensor, which could be falsified. So in this case, since we don't have any falsification of our sensors in the actuator attack case, we can see that this line, which is actually the black line for the actuators, is underneath this one. This is what the actual state trajectory is doing. So the actual state trajectory has the Lyapunov function increasing, which should be flagged if our attack detection strategy is working right. And on the right, we have the evaluated value of the Lyapunov function. This is also increasing because our sensors are intact. And so in this case, we would flag that attack and say, I could discover such an attack occurring. And we could look at other types of attacks and see if we would discover them or not. But the more interesting scenario is this case where we have a stealthy attack. So let's say that someone took over the actuator, and this is what they were really doing with it. They were actually making the Lyapunov function value increase. But at the same time, they took the sensor and they caused it to provide a sequence of values of the state measurement that would cause the Lyapunov function to decrease. So now this is very stealthy, and this is something that then we couldn't discover with our detection method. And this also helps us see some of the differences between the cyber attack and the fault, because it would be very unlikely that we have different components all taken over that are actually covering for one another if you just have a fault. They're like, okay, maybe you could have a sensor and an actuator fail at the same time, but the idea that the sensor would be actually covering for the actuator is something that is more specific to what you would think of someone doing maliciously than what you would think of as just like, oh, things just happen to all go wrong at once. So as the end of this part of the discussion about cybersecurity, I'll just highlight that our group has looked at a number of different things in addition to what was presented so far. We've looked at how could we make some of the theoretical guarantees that I talked about earlier in the case where you have these simultaneous actuator and sensor attacks, and we've done that by combining different detection strategies. We've also looked at whether combining those strategies could help us with detection and diagnosis of the attacks at the same time, and trying to expand the strategies into other ones where maybe we could detect attacks on all sensors that happen at once so that none of our sensors is intact anymore. So with that, I'm going to move into the quantum computing part of this talk. And I'm going to start by just giving a very high-level overview of quantum computing within process systems engineering and some of our objectives. And then I'm going to move into a little bit more about making the details of quantum computing a little bit more clear. So quantum computers are a new class of computing devices. They're under development, but some of the reason people are interested in them is they have potential for speed up for certain problems like finding prime factors of a number. In process systems engineering, which is the part of chemical engineering that I work within, people have been looking at quantum computing for some different applications, like how would it work for optimization or machine learning applications in chemical process applications, or things like how could it be used in chemical materials design. But our group has been focusing on this question: should quantum computers be used for any control tasks? And the reason we've been interested in this is because of this diagram shown earlier, where we said, well, the controller is running some algorithm on a computer. Today, it would be running it on a classical computer. So if we use today's computers to carry out classical control tasks, should we be using quantum computers for any control tasks? And the premise of what we've been looking at is that control engineers have taken a lot of advances in things like computing and networking already, and they've said which ones of these are useful for me, and then they've made those so that we have much better control strategies now than we did a long time ago. And so the thought is that, well, just as with those other ones that we needed to evaluate and then see if they were good for control, we need to do the same thing with the quantum computer. And so let's say that the answer is no, quantum computers aren't good for anything in control. Well, that's helpful to know, because then at least we would know not to keep researching that. But if the answer was, hey, we found an interesting application of the quantum computer for control, then of course we would feel very excited as control engineers, because now we would have a new tool for something that we didn't have before. So in order to try to move toward addressing this question, should quantum computers be used for any control tasks, we need to first think about what does it mean if a quantum computer is good for control. So we could start making a list. Maybe the first thing on our list might be, well, it should provide results to some control relevant problem faster than classical algorithms, but it should also make sure it doesn't ruin all the other stuff that we care about. Like, it should still ensure operational safety, it should still ensure that control objectives are met, and so forth. So one of the first questions we need to address is, does this first thing always happen? So are quantum computers always solving problems fast so that they will just provide results to any problem we want in control faster? And the answer is actually no. So quantum computers are not inherently fast. The cases where you get speedups are if you are very clever in your algorithm design. And so you have to use the quantum properties in the algorithm design. And these are things like superposition, entanglement, and interference. And the best way to think about this is that you have a classical computer, you have a quantum computer. Both of these are running on different physics, but both of them are trying to represent a computational problem. They're representing it, though, in different ways. And so because they're representing it in different ways and can take different paths toward this solution, if the quantum algorithm is able to take a path toward that solution because it has these special properties that the classical one doesn't have, that ends up being faster than the other one, that's when you would get a speed up. But this isn't like a guarantee that you can find such cases or that the quantum computer is just going to be fast because of that. So since we said the quantum computer isn't just better all the time, is it better at least for certain problems? So then we can say, well, it can be a little bit challenging to try to figure this out. So what are some of the reasons? One, today's hardware is actually not fault tolerant. So there are quantum computers today, but they are not fault tolerant yet. So they're what's called noisy devices. And this can make it more challenging to actually demonstrate the quantum computer being better at certain problems. And so the reason I say that is that, say that you have a classical algorithm, it will run and it will give the answer you expect. If you then were to use a noisy device, and let's say that the noise actually impacted your results, so now you don't have the result you expect, what's a fair way of trying to benchmark those two? One of them that's not quite giving the answer you expect and the one that is, and trying to figure that out. Then you could say, okay, well, maybe that might be hard sometimes, so instead let's think about theory. Well, if you want to do theory of when is one algorithm better than another, then you actually have to demonstrate that there is no known classical algorithm that could outperform your quantum algorithm. And that's really a high bar. And I would say in general in control engineering, that's not actually the bar that we put on most of our applications. Usually when we say, what's the best way of solving my problem, we would solve it several ways and say, this one was the best among the ones I tested, therefore this seems like a good strategy moving forward. Some of the other problems are that today's control problems that we wanted to solve already, we made them solvable in real time because that's how control has to be real time. So then the question about what can quantum computers offer would sort of be, what are the problems we have left behind and said those ones we can't do and we don't even want to try. We just left them as so challenging that we didn't even bring them to the real-time domain yet. And then we have to ask the question of, could quantum computers help with those problems? What problems are those and how could a quantum computer help with those? Or we could say, maybe we shouldn't be thinking about online. Is it actually offline control computations where it could be helpful? So we can see from this that a lot of this first step we need to take toward evaluating whether we should use quantum computers for any control tasks is actually, how should we approach the search for the control relevant problems where a quantum device could have utility? And so there's many ways you could approach this, and some of them are what I mentioned earlier. Like one way you could do it is try to say, I'm going to try to attempt these simulations and try to figure out if I can fairly benchmark things. I'm going to try to instead find problems in control with significant computational complexity challenges and then try to define a control objective where it would not be fine to do something like learn the control law and just say, well, now it's really fast. I used machine learning and now I learned the answer. And so those are completely valid ways of approaching this. The way we have been trying to approach it is more of trying to see if there's any no-go situations from a safety perspective that would indicate that the quantum computer is not going to be effective, or that we would have to modify algorithms in certain ways in order to make it effective. And we've been hoping that by exploring how the quantum devices or algorithms would influence satisfaction of our control objectives like safety, that might help define certain paths toward what might be some of the uses of quantum computing. And so this is because we consider safety will always be a control relevant objective, and that there are these significant issues that could impact safety with quantum algorithms. So one of those is that today's hardware is noisy. We hope that we will get fault tolerant quantum computers, but until we do, are we able to use today's for any control calculations, yes or no? And then also, even if we do have perfect quantum computers, a lot of the algorithms that are run on these have some level of non-determinism. And that's actually because if you're going to use the quantum properties of the quantum computer, you probably are wanting to place your states in superposition. And when you measure a superposition state, that's where you introduce probability. And that's just a fundamental part of quantum mechanics. And so because of that, then you will often have non-determinism in the algorithms. And so what we're hoping is that by analyzing this safety perspective, that it will give us some results that will guide our next steps in evaluating quantum computing for control. And so now I'm going to give a little bit more details about how the quantum computer works. So quantum computers have circuits, and so here's a little picture of a circuit. And the idea is that quantum circuits involve you have your qubits, and those are in a quantum state. And so the quantum states can evolve with time and be controlled. And so the quantum state is represented by this interesting notation, het psi of t, and this is what's called Dirac notation. And we only want to have two possible quantum states for the system so that each qubit can represent only two quantum states. And so this is so that we can work with binary. And so how does a quantum algorithm actually work? Well, you could really think of quantum algorithms as dynamic systems manipulation. So the idea is that you will start your quantum state, your qubits, in an initial condition, het psi of t0. Then you will evolve the quantum state with time. and it will obey the Schrodinger equation, because that's the dynamics of the quantum system. Then, if you're wondering where do gates come into this, well, you can think of this as the discrete time version of the dynamics are being represented by gates. So essentially, the quantum state at some next time is equal to your gate times the quantum state at the prior time. And this gate is related to, if you were to solve this equation, then it would be the time evolution would be represented through this matrix here and how all of this works together. So then at the end of your quantum algorithm, you measure your final state. And when you measure it, the measurement should be related to the solution to a computational problem if you set up your algorithm in a good way. So algorithms on quantum computers are then represented as circuits that consist of blocks of gates called quantum gates. And these implement the logic operations. But as we noted, the gates are really sort of the matrix that helps you represent the discrete time version of Schrodinger equation evolution. And so they will have some constraints on what's an allowable gate based on the physics of how the Schrodinger equation constrains quantum state evolution. So that would include things like the gates have to be unitary. And so when you have a finite sized quantum system, which like we said would be ones that we're going to use for quantum computing because we're going to only want to have two different states, then you can represent the quantum state using vectors, and you can represent the operations on it, so the gates, using matrices. So this is an example of what's called a Hadamard gate. What this does is it will take a qubit from its initial state and then move it into a superposition state. And then this identity gate would mean you didn't really do anything to it. Then you can also make NOT gates. You can make things like a controlled NOT gate, which would be this one, which will flip the qubit state if the control qubit is in a certain condition and so forth. And so as was mentioned, at the end of every quantum algorithm, the final state is measured to determine the results of the algorithm. This is where probability comes in. So quantum state evolution is deterministic, but then when you have measurement is where probability will come. And so this is because if we represent our quantum state, let's say we represent it as a vector, as was mentioned that this is possible to do. Let's say that it is a 2-bit system. So we'll have, these are my options of what I could measure from this quantum state. I could get 0, 0, 0, 1, 1, 0, 1, 1. And so in this case, all of these numbers that are here are what are called amplitudes. So if I take the complex magnitude squared of this number, it represents the probability of measuring 0, 0. And if I take the complex magnitude squared of the next number, it represents the probability of measuring 0, 1, and so forth. So you can see that, like, for example, in this example, the probability of measuring this state 1, 1 is 37.5%. And so we can string together lots of quantum gates and then perform measurement at the end, and we can get different algorithms. And so this is an example of an algorithm that actually performs addition using something called the quantum Fourier transform, which is shown here, and then you have some rotation gates, and then there's the inverse of the quantum Fourier transform. But what this does is it takes two integers, a and b, and you have their binary representations. Then you perform all these different gates, and at the end, what you get back is the binary representation of their sum. And so that's the background on quantum computing that I'm going to give. Now I'm going to highlight some of our results in looking at quantum computing being used for implementing control and some of the preliminary work we've done so far and what we found. So in this case, the problem that we're going to be talking about is the issue of quantum computers being noisy today. So this means that the results of a series of gates might be non-deterministic in practice, even if, for example, they should be deterministic in theory. So if control was implemented on today's quantum computers, that could mean that I might expect to apply a certain input to my system, but I'm applying a different one. So this raises the question of when could control be implemented on a quantum computer? Is this going to be completely destructive to safety? What will happen? So in order to start an initial study of this, we looked at a very simple dynamic system. In this case, x dot equals x plus u, and u here is going to be -2 times x. So this would be stabilizing if we were able to implement it exactly. But now we're going to look at, well, what happens if I can't implement this always as -2x because the control actions might not be correct because I'm using this noisy computer in order to calculate it. So what we're going to do is explore the implications of this for safety. And I want to highlight not for speed. I'm not saying that this is a good application of a quantum computer. I'm not saying that this is a speedy algorithm compared to just doing addition, for example, on your normal computer. I'm just trying to say that we are looking at this from a safety perspective. And so in order to try to make these initial simulations, we had to figure out what are we going to use to do the simulations. So at the time that we did this, IBM had some free quantum devices available on the IBM Quantum Experience if we were to log in, but those only had 1 qubit and 5 qubits. And so we didn't think we could really run a control relevant simulation with 1 or 5 qubits. So instead, there was a 32 qubit quantum simulator available at the time. And this is what we decided to use. So just a few notes on that. A quantum simulator is not actually a quantum computer. A quantum simulator will be a program that you can run on a classical computer in order to have some types of simulations effects related to the quantum computer. And so what this means is 2 things. 1, it doesn't have any noise. It's not actually a quantum computer. You have to add a noise model if you want to try to see some effective noise. And then, of course, there will be some level at which this is model dependent. And then second, this also means that the quantum simulator's runtime has nothing to do with the runtime on the actual quantum hardware. It's not a quantum computer. It's just a simulator being run on a classical device. So where we're going to use the quantum algorithm is in this u equals -2x computation. We're going to use the addition algorithm that I mentioned in order to calculate x plus x. And that addition algorithm is actually deterministic. So anything that we see here that isn't, we can say is coming from the noise model that we added. So here we're going to make a comparison, and this is between using a classical computer in order to compute x plus x, the quantum simulator with no noise to do that, and then the quantum simulator with noise to do that. And so here we see our process states in dimensionless time, and our process inputs also in dimensionless time. And what we have is that the ideal quantum system, so no noise, and the classical system have overlaid results. And that's because, as mentioned, the addition algorithm is deterministic. So this is exactly what we would expect without the noise. But then when we added the noise model, we started seeing that the state started jumping around more because the inputs were, but in our simulations, it still went toward a neighborhood of the origin. So this was curious to us. Of course, this may be noise model specific. Of course, this could be realization of the noise specific. But this caused us to think, I wasn't expecting it to behave quite so nicely. So does this mean that we can develop a theoretical understanding of when noise in the quantum computer does not disrupt safety to help us try to get closer to explaining this result and what might be the limits of what we can and can't do with the quantum computers that are noisy? So as our start toward analyzing this, we looked at this discrete time, linear time invariant process, which is shown here. And we said we're going to have this be our chemical process, so to speak. It says that x at the next time is equal to this a x of t plus b u of t, where x is our state and u is our input. And so we're going to have that x of t plus 1, if we didn't have any type of input, would be a x of t, so we could write explicitly that x of t would be a to the t times x of 0. So we could say, okay, what might be our potential goals? So of course, we could want our state to be bounded for all time. We also might have goals and control, things like, okay, well, instead I want the state to go toward the origin as time goes to infinity, and I could do that by doing things like making the complex magnitudes of the eigenvalues be less than 1. So our question here is going to be, how can I use control theory like this to guide our understanding of how good quantum computers need to be before they can be used in control action computation, because they must operate our process safely if we would be interested in using them. So in general, we wouldn't expect that we can drive the norm of x of t to 0 if we have noisy inputs. But our question could be, could we ensure that the norm of x of t is less than an upper bound for safety purposes? So we're going to apply the control theoretic principles for linear time invariant systems that are under bounded disturbances. And in this case, we have our process, and there's a sensor. Then we'll have the quantum device being used to compute a control action like -kx of t. And so what we'll get to the actuators is u of t plus this delta. And delta here represents our quantum noise. So it represents we should have computed -kx as u, but instead we computed something that's -kx plus some other amount of stuff. And so now we can look at the dynamics. So in open loop, we would just write this as x of t plus 1 equals a x of t plus b u of t. And then our desired input here could be u of t equals -kx of t. And then our input resulting from the noisy computation could be this -kx of t plus delta of t. So delta is our computation error. How big can it be? Well, if you have a finite register size on your quantum device, then that places a bound on how big it could be. But if you have a large register, then it could be quite big. So then we can write the dynamics by actually plugging in this to represent the closed loop dynamics explicitly. So we get x of t plus 1 is a x of t minus b k x of t plus this b delta of t. And that's what we have down here for our process. And so then we could say, okay, well, if I didn't have the noise from the quantum computer, then I could try to make it so that the norm of x of t would go to 0 as t goes to infinity by making the complex magnitudes of the eigenvalues of a minus bk less than 1. And then so what would that give me? So then we could say, okay, well, with the noise, you could make the norm of x and you could look at how it's upper bounded. You could say, well, as time goes on, eventually I would kind of get my state within this certain norm ball. And I could say, okay, well, this upper bound is related to how big the maximum value of my computation error is. So that might sound good at first, like, great, our process state is bounded. So then maybe it would look like this. We have this bound and our state's jerking around, but at least it was bounded. But this still might not be good at all because process safety is going to be dictated by the equipment limits. So let's say that these were the equipment limits and this was the bound that we calculated in this expression, then now this isn't so great. So boundedness of our state doesn't imply safety. So does that mean that we're done for? And so we can't use any noisy quantum device? Well, we could try to then see if we could explore how theoretical studies might be used to help us define device requirements that might help us meet our safety metrics. So this is just a small example, but let's say that we wanted to use this kind of weird input policy where initially we use this input and then at the next sampling time we use this input and then the next time we, and thereafter we use these. These ones, u of I, are dependent on the prior realization of this computation error. And then this would give us the closed loop dynamics after a certain point that it's dependent on the computation error. So then this helps us to directly relate our state and the computation error. So if, for example, we wanted to specify that our desired result is that the norm of the state is less than or equal to an upper bound nu with a certain probability, and we said, if the computer could achieve that for me, I will use that computer. Then we could use this expression and say, okay, I'm going to take the norm on both sides and then rearrange things. And now I can place a bound on how the noise has to act. I can say, okay, well, then the noise realizations have to be less than or equal to the nu that I want to specify divided by the norm of the matrix B, the required percentage of the time. So in this case, we used control theory to provide an explicit requirement on the noise profile that we would accept from the quantum computer. And so this can help us to understand whether a noisy device or algorithm combination would meet the mark that we want for us to be able to use it. And then I'll just highlight this last point. Does control theory also impact quantum algorithm design? As I mentioned earlier, quantum algorithms can have non-deterministic results. And so we actually have done a good deal of work related to this as well, trying to look at some of the control theory. And I would say the highlight of what we learned from this was that you can actually then probably in the future find out ways to design your quantum algorithms with the control theory in mind to try to make it so that there's very low probabilities that they output certain problematic control actions, and that would be a direction of future research for us because we think that that could be impactful at being able to ensure safety using these non-deterministic algorithms. And so in conclusion, next generation manufacturing values flexibility and profitability, and it's facilitated by automation advances such as economic model predictive control. Flexible and profitable systems may not be secure, and attacks on control systems could undermine process safety. So we've looked at things like integrated detection and control policies that are geared toward nonlinear systems because these have potential to enable attacks of various types to be detected before they cause safety issues. But some of the downsides of this could be that what we've done so far requires sufficient control theoretic conditions in order to be able to guarantee that attackers can't get the upper hand in certain situations. And they also might require certain considerations on the process, like that at least some sensors were secure. And so there are also fundamental notions of cyber attack resilience and discoverability for nonlinear systems, and these provide insights into potential future directions for securing the controllers. Quantum computing provides another interesting potential direction for the future of next generation manufacturing, but it really requires further exploration to determine if benefit exists for quantum computing implemented control. We've been taking one direction toward trying to figure that out, and the direction we've been taking really focuses on trying to analyze what would it take from a safety perspective to make these useful and to make sure that there's not any no-go consideration from the safety realm. But then, as was mentioned earlier, there are many other directions that should also be taken, such as when can we theoretically find problems that would be important for the quantum computer to solve, and how could we start to benchmark them more from a simulation perspective. And so some of the work today was presented by some of my great students. and postdoc who have either now graduated or are still in the group. And I'd also very much like to acknowledge our sources of financial support. And I'd really like to thank everyone so much for taking your time late on a Friday afternoon to hear this talk. So thank you so much. I'll be happy to take any questions.
Time for questions. I can start. So I have two questions. The first is one thing I'm trying to wrap my head around. So you are using a noise model in the computation, but you also mentioned when you measure things, there's a probabilistic output by the nature of this quantum machine. When implementing these controllers, do you need any measurements, or is it like, should I think about it as an analog controller where nothing is measured, but like wires are going in, or like why you don't have the probabilistic part that comes from the measurements? Maybe.
Oh, you mean in the example where I said that the algorithm was deterministic? Do you mean like how this algorithm is deterministic, so that when I was talking about the example with the noise, I was saying let's only focus on the noise?
Yeah, so my question is that I want to implement a control action, and there's this quantum device, and it looks like you are not taking an observation or measurement from the quantum device. Is that the case?
So every quantum algorithm will end with measurement of the qubits, because you have to somehow extract the result out of the system, or else you don't know what it computed.
Okay, so my question is then how you are using that probabilistic nature of the measurement in your analysis?
Yeah, so in what I presented here, I was actually focusing on the noise case. So this algorithm, it's not necessarily true that every single quantum algorithm is non-deterministic. I think a lot of valuable algorithms will be non-deterministic. But this algorithm actually is deterministic. So there would be like 100% probability that you get the correct sum from this algorithm that you should have gotten. So this algorithm won't have that issue with like, oh, what would happen if I accidentally got the wrong number? There would be like, you would just get the right numbers as long as you don't have noise. So if the algorithm acts according to how it should. So then in what I presented here, I was focusing only on the noise part. And so sort of separating these two issues, saying like, okay, there's noise, there's also non-determinism due to the algorithms, even if the computers have no noise. Let's separate those two and just look at the noise part. But then what I was mentioning at the very end down here, like how would control theory impact quantum algorithm design? We have also done some work where we said, okay, what if it's not noisy? And what if instead the algorithm is non-deterministic? And then what we did with that is so far, we looked at saying, okay, let's say then that if you have a certain probability of getting the right answer that you expected, then the probability that you stay safe is at least as much as the probability of getting the right answer. Probably we need to start looking more at stochastic systems, perspectives and stuff to try to get a better thing. Than I think the deterministic answers are sort of challenging. But I think that that's where our idea about what we really should be doing, though, is probably making the quantum algorithms have control in mind. So if we said, okay, if it was actually going to be unsafe to apply some of the control actions that I might probabilistically get, how could I make it less likely through the algorithm design that the output would actually turn out to be one of those bad ones? So maybe there's like several control actions I could still get, but if I could force those ones to be ones that would all be okay if they were applied, then I think that that would probably be like the best way of trying to handle this would actually be to go back to the quantum algorithms and start adjusting them to get answers that are okay.
Yeah.
This example is like an online study about quantum computation. You referred to there may be a lot of offline things. We do lots of like Monte Carlo simulations and things like that. So can you just talk briefly about like what are some thoughts that you have about how you might use quantum computing offline for control design or analysis?
I feel like I have ideas about this, but I don't feel like they're well formed enough for me to like really say something that's intelligent. And so I don't want to say something that's like really crazy. But I think that certainly that if you want to find the good offline applications, then what I can say is I think the best ones to look at if you want to be able to prove something theoretically about them would be ones where you could say like, oh, it has this really bad computational complexity, even for the best known classical algorithm. And then that's where you would say, okay, well, now I want to see if quantum theoretically could do better than that. And then that would be one good way of doing it. Now, if you just want to try to test out ideas, you could look, there's a lot of quantum algorithms in the literature already, but I think there's many more to be discovered. So if you wanted to see, for example, like, oh, is there an algorithm that maybe is a quantum version of something that's of interest to you? you could see, and then you could try to implement it and then see if you could do a fair comparison. Like, even though today's quantum computers are not perfect, you could see if you thought there was a fair comparison. But otherwise, if you want to do it at theoretical level, I think then you should find ones that have very bad computational complexity analyses. Yeah, thank you.
I have one more maybe naive question. So these, you mentioned you were using like quantum computer simulators. Did they implement floating point arithmetic or like, because you said, I think 32-bit simulator, do they like have this floating point arithmetic or is it more like fixed precision?
That meant that it was going to simulate a 32-qubit machine. So like that the quantum computer it was simulating would have 32 qubits. So that didn't mean that the simulator is only capable of itself using 32 bits. If that
is like, should I think about like, since we are using 32-bit qubits, is the fair comparison with fixed precision arithmetic 32 bits? Or because like you can have a classical computer that has just fixed precision arithmetic that was implementing floating point.
I will say I am a little less knowledgeable about all the like floating point and things probably. But I think what we were comparing in our simulations was for both simulations on the classical computer and then the simulator, what we would do is we would take the number from the sensor and then we would like multiply it by, I think we would like round it, multiply it by 100, and so turn it into binary numbers in both or in the quantum computing case. And then in the other case, we did something that was similar in order that it would be like truncated. I think we rounded it so that we were trying to do like something fair, at least in terms of the simulation of saying like, well, both cases, the measurement that's being received essentially by whatever's going to compute is like the same number of bits long. And then, but yeah, we didn't do more than that, than making sure that the sensor and sort of what we output, then we would like also like post-process it, but we didn't do something in the middle besides that.
Final questions? If not, let's thank the speaker again.
Thank you.
Yeah.
Wow. See you in